In part 2 of this lecture, we're going to talk about the t-distribution and confidence intervals for proportions. So recall that when we calculated the standard error, we needed to have the population standard deviation in order to use it in the calculation. The problem is we don't always know the value of the population standard deviation. However, we can estimate it. Assuming that the sample size is large enough, that is, we have a sample size of at least 50 cases, the sample standard deviation is a good estimate of the population standard deviation. So we can calculate the estimated standard error, S sub y bar, by using the sample standard deviation, S sub y, in the numerator, and using the same value in the denominator, the square root of n, to get the estimated standard error. However, estimating the population standard deviation with the sampling standard deviation creates a problem. It introduces additional sampling error, and we need to take into account the additional sampling error because that's going to throw off our estimates a bit. In cases like this, we use something called the t-distribution rather than the normal distribution. So the t-distribution is a family of curves that follows a slightly different shape depending on their degrees of freedom. And so there's a different curve corresponding to different degrees of freedom. And the t-distribution resembles the normal distribution. That is, it's approximately bell-shaped. However, the t-distributions tend to have fatter tails, or more of their area in the tails, less of their areas in the middle, depending on their degrees of freedom. And so, the degrees of freedom are calculated as the number of cases, n, minus 1. We lose 1 degree of freedom because we're estimating the true population standard deviation with the sample standard deviation. However, as the degrees of freedom increases, the t-distribution more and more starts to resemble the normal distribution. And basically, at large sample sizes, the two are the same. So this figure illustrates a comparison of the standard normal distribution to the t-distribution for several different degrees of freedom. So notice that the solid line shows the standard normal curve, or what we could consider degrees of freedom being large, shown here as infinity. Notice that the curve has less of its area at the tails of the distribution and more of its area in the middle. The next curve, which is shown as the gray dashed line, shows a t-distribution for 10 degrees of freedom. Notice that its area has more of its area in the tails and less of its area in the middle. And we can see as the degrees of freedom drop from 10 to 5 to 1, we basically see that more of the area is in the middle at the tails of the distribution, less of the area is in the middle. Okay, so when we're dealing with the t-distribution, we actually use something called a t-table to find a t-score corresponding to some area under the t-curve. So the t-table is organized slightly differently than the standard normal distribution. That is, it has less numerical detail. And instead of showing you all of the different areas corresponding to all different z-values or t-values, it only has areas for particular t-scores. And it does it separately for different degrees of freedom. And so here's an example of a t-distribution. And so notice that we have different rows. Each of these different rows corresponds to a different degree of freedom, or a different curve. And so here's the row corresponding to 1 degree of freedom. And then it has columns corresponding to different levels of significance. And so here's the column corresponding to a value of 0.025 or 0.05, depending on whether we have a one-tailed or two-tailed test. And so we can see that there's actually values for one-tailed tests and two-tailed tests. And so because when we're dealing with a confidence interval, we split the alpha risk in half. That is, half of it's in the left tail of the distribution, half of it's in the right tail of the distribution. All confidence intervals that we'll calculate are going to be using the two-tailed alpha level. So in this case, we want to look at the 0.05 for a two-tailed to get the t-value that we need for our confidence interval. And so here we see that the t-value for 1 degree of freedom, 0.05 alpha level, two-tailed, is 12.706. So that's the value that we're going to use. And so the formula for calculating a confidence interval involving a t-value is a little bit different from the formula we saw before, but it has the same basic format. And so the confidence interval is equal to, again, the sample mean, y bar, plus or minus the product of a t-value instead of a z-value, multiplied by the estimated standard error, S sub y bar. And so as an example of calculating the confidence interval, we're going to look at the example of the mean of the father's education, and we're going to use some data from the 2012 GSS, a random sample of only 25 cases. Based on that sample, we know that fathers, on average, have about 11 and a half years of education. And we have a sample standard deviation of 3.46 years for fathers. And so we can calculate the estimated standard error. And we do that by taking the sample standard deviation, in this case 3.46, dividing it by the square root of our sample size, or the square root of 25, or just 5. And that gives us a value of 0.693. So notice that we have a fairly large standard error here, almost an order of magnitude larger than the ones we've looked at before. Okay, since we estimated the population standard deviation with the sample standard deviation, we have to use the t-distribution rather than the standard normal distribution to account for the additional sampling error. And since we're using a 95% confidence interval, we need the t-value corresponding to a 0.05 level of alpha for a two-tailed significance level. So first, let's find our t-value for a two-tailed test, 0.05 alpha level, and our degrees of freedom. And so notice that we have 25 cases. We lose 1 degree of freedom. That means we're down to 24. However, the table does include a value for 24. So we're just going to use 25 because it's the closest one. And so that means that our value is going to be 2.06. So it's a little bit bigger than the 1.96 that we used last time. But notice that if you look at the bottom of the table, for a large sample size, it would be equivalent to 1.96, which is what we used previously. Okay, so now we just plug the numbers into our formula. And so we plug in first our value for the sample mean, in this case y bar, the value of father's education in this sample of cases, which is equal to 11.52. And then we add and subtract the product of our t-value, 2.06 in this case, and our standard error, 0.693. And so when we multiply 2.06 times 0.693, we get a value of 1.43. And then when we add and subtract that to the value of the sample mean, 11.52, we get a range of 10.09 to 12.95. And so how do we interpret that? Well, we say that we're 95% confident that the true father's education average, that is, the father's education average in the population, is no less than 10.09 and no more than 12.95. So we can see here that we have a range that's just a little bit above 10 years of education and a little bit below 13 years of education. Now let's talk about confidence intervals for proportions. So we've been using confidence intervals to compute values for sample means, and that's fine if we're using interval ratio variables. But what happens when we're dealing with nominal or ordinal variables? Well, we can turn that information into proportions and then calculate a confidence interval for proportions. And so we can compute confidence interval for sample proportions and their estimates of the value of the true population proportion. So conceptually, the same foundation that's used for a sampling distribution of means can be used for a sampling distribution of proportions. Both use some kind of a confidence interval, and both have a sampling distribution. In the sampling distribution of the proportions is this thing that underlies the population proportion used as an estimate of the true population proportion. Okay, so the central limit theorem tells us that the distribution of proportions is approximately normal, with the following mean and standard error. So we can see that the mean of the population proportion, the mean of the sampling distribution, that is equal to pi. And here I'm using pi to represent the true population proportion. And we can also see that the standard error of proportions, which I'm calling sigma sub p here, is equal to the square root of the quantity of pi, the true population proportion, times 1 minus pi divided by n. Okay, so from the standard error formula, we see that the following is true. So first of all, sigma sub p, which means the standard error of proportions, is equal to the number of cases in the denominator and pi in the numerator. And again, this is not the number 3.14. It's a symbol used to represent the true population proportion. So don't let that confuse you. Now there's a problem. Unfortunately, we don't know the true population proportion. In fact, that's the very thing that we're trying to make an inference about. And so we have to do something to figure out some other value to use for the true population proportion. And so the solution there is to use the sample proportion as an estimate of the true population proportion. So we're going to use p, the sample proportion, to estimate pi, the population proportion. And so that gives us the estimated standard error formula. And in this case, we're going to call that S sub p. And that's equal to p, the population proportion, times 1 minus p, divided by n. And that quantity is taking the square root of. And so we basically have an estimated standard error of proportions. And because we've used the sample proportion, p, as an estimate of the true population proportion, pi, we've introduced additional sampling error. And again, we have to use the t distribution to take that into account. And so here's the formula for a confidence interval for proportions. So you can see that p stands for the sample proportion. T is the t-value corresponding to our desired level of confidence, with degrees of freedom equal to n, the number of cases, minus 1. And then S sub p is the standard error of proportions. As an example, let's consider the proportion of cases that with a bachelor's degree. So suppose we had some data from the 2012 General Social Survey. We had a sample of 1,974 cases, and we found out that 17.93% have a bachelor's degree. In other words, p is equal to 0.1793. Let's create the 95% confidence interval for the true population proportion of people with a bachelor's degree. And so here, because we have a large sample size, 1,974 cases, we can use a t-value that would be the same that we would use for a normal distribution, in this case 1.96. So t is going to be 1.96. Let's start by calculating the standard error of proportions. And so we would plug the numbers into our formula. So we have to calculate it by taking p, in this case 0.1793, multiplying it by 1 minus p, and then dividing it by n, the number of cases. And in this case, that's 1,974. When we do all the arithmetic, after we take the square root of that value, we get 0.00863. And so we've got a fairly small standard error here. And so now we can plug the numbers into our formula. So for calculating a 95% confidence interval, we take our sample proportion, p, again, which is 0.01793, and we're going to add and subtract that to the t-value for a large sample, that's 1.96, multiplied by our standard error of proportions that we estimated, which is 0.00863. We multiply those two together to get 0.0169, and then we add and subtract that to our sample proportion, 0.1793, and we get a value that ranges from 0.162 to 0.196. And so how do we interpret that? Well, we can say that we're 95% confident that the true proportion of people with a bachelor's degree in the population is no less than about 16% and no greater than about 19%.